Today's speaker, Professor Jess McIver.
Thank you very much, Simone, and thank you very much for handling questions, Ben. So it's wonderful to be here today, and I'm really looking forward to sharing this research with you. So I'm joining you from the University of British Columbia, which is situated on the unceded and historical territory of the Musqueam people. And today I'm going to be telling you about gravitational wave astrophysics, so a subject very near and dear to my heart, and also something that's really exciting to be involved in as someone who's learning about physics. So there's a bit of construction around me, so if it starts to get loud, please jump in and let me know, and I'll see what I can do about that. And I'm really looking forward to your questions, so keep those questions coming. You're welcome to put them in the chat during the talk, and if I spot them, then I'll do my best to answer. And then, as Simone said, we'll have plenty of time for questions after the talk. Okay, so let's go ahead and dive right in. So the context of gravitational wave astronomy is that we've learned most of what we know about the universe with light, with photons and electromagnetic radiation. So we've learned about the expansion of the universe. We've learned about dark matter with clues that we get from light. But gravitational waves are really special because they are very, very weakly interacting ripples in the fabric of space-time itself. And what this means is that unlike light, gravitational waves are going to be able to propagate through vast distances, effectively completely unaltered. So we're going to be able to get this crisp signature of whatever the dynamics are, the systems that are generating gravitational waves. So unlike light, gravitational waves are going to travel straight through the Earth. So we're going to be able to detect them any time of day or night. We're going to see them travel through galaxies, through billions of light years, essentially carrying exactly that same signal that was produced from the source. So let's learn a little bit about where they come from. So what makes gravitational waves? So there's an equation here that's describing the amplitude of a gravitational wave, which are again these ripples in space-time itself. And there are three things that I want you to notice about this equation. So this is the amplitude of space-time strain, so how much we'll see that space is stretching and squeezing. But for now, we're just worried about what's generating these waves. So this amplitude of the wave is directly proportional to a very small number divided by a very big number. So first off, our intuition is that this number, the strain, should be very, very small. And it turns out that this is indeed the case. So we expect it to be small. The next thing I want you to notice is related to this term. So this is the acceleration of some asymmetric distribution of matter. So we call it this quadrupole moment here. So the second time derivative of the quadrupole moment. And what this is telling me is this: if I have some system that has some asymmetry and that it's in motion, what I'm going to see is a gravitational wave in space-time. So if I have something that's perfectly spherical, I'm not going to see a gravitational wave if I move it around or if it's spinning. However, if I introduce even some really, really subtle asymmetry, so add, for example, a mountain on the surface of a neutron star in the order of a millimeter, I will expect to see gravitational waves if I start to orbit that neutron star. So other sources that you may have heard of in the news are, of course, the Inspiral and merger of black holes and neutron stars. So we'll talk about that a little bit more. And the very last thing that I want you to notice about this equation, so I know that it's related now to this asymmetric acceleration of matter. I know that it's going to be really small. And then the last thing is that it goes, the strength of the signal goes as 1 over the distance. And this is, again, really different from light, from electromagnetic radiation, where if I'm measuring the strength of my signal with light, if I'm counting photons, the flux of photons in the area of a photodiode, for example, the strength of my signal is going to go as 1 over r squared. But here now, if I can measure them directly, and we'll see that we are able to do this, the strength of my signal is going to go as 1 over the distance between me, the observer, and my source. And this is going to allow us to see gravitational waves at really, really vast distances into space, which is really exciting. All right, so now that we have a sense of how one might generate gravitational waves or how they're generated in nature, let's get a sense of some of the common sources that we see of gravitational waves. So if we had a perfect telescope and we could zoom way in on two black holes that are roughly about 30 times the mass of our own sun, this is what we would see. So we can see these black holes are orbiting, they're getting closer and closer together, and this wobble of the star field behind them. So that's the propagation of the space-time distortion that we can measure as gravitational waves. So let's take another look at the same system. And now instead of using light, we're going to use gravitational waves. So this is again two black holes, roughly 30 times the mass of our sun. So these could be generated from the collapse of massive stars. And now what we're seeing in this field is the curvature of space-time. So as the colors go from blue to orange and to red, what we're seeing is this increase in the distortion of space-time due to the presence of this mass here. And this time series on the bottom, so this is actually tracing out the amplitude of this gravitational wave. So as these black holes are orbiting each other, what we expect to see from this prediction of general relativity is that they're getting closer and closer together until finally they start to merge. So this is where their amplitude is at its peak. And we expect to see that up until this point, the frequency of the merger of these gravitational waves is increasing more and more. And this is because they're radiating away energy in the form of gravitational waves that's causing the orbit to spin up until they merge. And then that gravitational wave signal propagates out at the speed of light. And it carries so much information. We have within this, we call it the Inspiral signal. As those two black holes are orbiting, we can tell their masses, we can tell their spins, we can tell something about how they're oriented relative to each other and to us, the observer. And then this merger and ring down allows us to test general relativity and a lot of really rich physics that we can get from the signature of these systems. So how do we measure this? So let's say we have a system that's producing gravitational waves. So there's something out there in space that's causing a gravitational wave signal that looks like this. Maybe this is two black holes that are really stable part of their orbit. Maybe this is a spinning neutron star with some small asymmetry to it. But I have something out in space that's generating the sinusoidal signal. So that's the strain that's being produced. And this is related again to the distribution of mass and how it's moving. That's what's generating my gravitational wave strain. And then what happens as that gravitational wave propagates? So this is what we're seeing here. So as this gravitational wave passes into or out of the screen of your laptop or whatever you're using to watch this, this lecture, what's happening is that space-time is getting stretched and squeezed in two orthogonal directions. And if we measured any 2 points, let's say we take these two middle points here, we can relate this gravitational wave propagation to the change in length over the length between those two dots. So when there's no relative change in motion, so I'm just looking at the trace of these two dots, so this is my L, then I can calculate the strain by the difference essentially between this direction, so the X direction here, and the Y direction. And if I divide that by my length, then I get my strain. And you might notice that the farther apart my dots are, the more sensitive I can be into those relative changes in length. So this is why we're going to see that we build detectors that are really, really large in scale. And this also motivates, because we know that strain is going to be affecting two perpendicular directions, this motivates the choice of two orthogonal detector arms. So let's take a look at a gravitational wave detector, and we're going to see this in action here. So here we've got these two perpendicular arms that we're going to use to sense this relative motion. And the way that we do that is that we have this input laser. So this is coherent light. And what that means is that the light is all in phase. And this is really important because I'm going to be using the wavefronts of this laser light essentially as a timer to time how long it takes light to cycle in one arm relative to the other. And the way that it works is that this coherent light makes its way to what's called a beam splitter. So the light is then split in two orthogonal directions, so 50% of the light in each direction, and it's going to travel down each one of these arms. And if there's no gravitational wave in my detector, then what I'm going to see, based on the way that I've arranged my detector, is that this light's going to interfere. It's going to deconstructively interfere and pretty much nearly cancel out at my output photodiode. So I'm not going to see any signal if there are no gravitational waves. However, if I introduce a gravitational wave that's coming into the plane of my detector, I'm going to get this relative change in length. The space-time is going to start to be stretched and squeezed in these orthogonal directions. And I'm using the light that's traveling in the interferometer, I'm timing it relative to the other arm. So I'm essentially timing how long it takes the light to travel down my one arm relative to the other. And this is actually going to let me directly read out as this interference pattern, this subtle difference in phase between my coherence lights, this strain amplitude. And this is actually real data from the very first Nobel Prize winning detection of gravitational waves. And we have a network of these detectors all over the Earth. And again, remember that's the longer the distance between the two dots we were using to sense the relative change in length, the longer that distance, the more sensitive my measurement is. So we actually build these detectors on the scale of kilometers. They're enormous. And let me show you where they are around the world. So we've got two LiGO detectors in the US. Each one of those arms is 4 kilometers long. So they're really quite giant, but they operate essentially with the same principle that we saw on the last slide. We've got that coherent light coming in, it's split by a beam splitter, and then it cycles for in these 4 kilometer long arm cavities to help enhance that signal. We also have a 3 kilometer detector in Italy called Virgo. All 3 of these detectors were online in the last observing run, and I'm going to show you some results from that observing run. We also will have other gravitational wave detectors online around the world, so Kagura in Japan and LiGO India, which will be a 3rd LiGO detector in India. All right, so let's put this all together. So let's say I've got 2 black holes, they're orbiting each other in space, they merge, and that signal is sent as a gravitational wave at the speed of light throughout the universe. So for the first detection, this actually traveled for over 1.4 billion light years before finally reaching Earth. And now we're going to see, I'd like to emphasize that this is really exaggerated, but as this gravitational wave is passing through the Earth, you're going to see the stretching and squeezing effect. Of course, it's much, much smaller than this. The Earth doesn't actually bob around like Jello. But as this gravitational wave passes through the detectors that are on the surface of the Earth, the space-time is still going to be stretched and squeezed, and we're actually going to see this stretching and squeezing as this difference in phase between the 2 arms. All right, so with this in mind, so let's talk about a really special kind of signal. So we've talked a little bit about black holes. So we've measured quite a few black holes now, and I'm going to give you a little bit of a tour of those. But I want to tell you a little bit about another really, really special kind of signal, and this is the merger of neutron stars. So this, in terms of gravitational waves, looks pretty similar to us. So we're going to see what we expect from general relativity. Those 2 neutron stars, as they're orbiting each other, they're going to get closer and closer together. So the frequency of that gravitational wave signal is going to increase over time. So that looks pretty similar to black holes, except for when they get really close together. So when you get 2 neutron stars that are about the same distance apart as their diameter, they're going to start to tear each other apart through tidal forces. And this is going to, as they merge, make this really, really spectacular effect that we're going to see all throughout the electromagnetic spectrum. And this is the first example of multi-messenger astronomy with gravitational waves, where we had a spectacular light signal in concert with gravitational waves. So this was detected back in 2017, and I'm going to show you a simulation of what this looks like. So here we've got 2 neutron stars. They're emitting gravitational waves. This is just through the dynamics of their orbit that we're seeing this gravitational wave signal. They're going to start tearing each other apart until they merge. We're going to see a burst of gamma rays. And then as this really, really rich neutron matter interacts and evolves, we're going to start to see what we call a kilonova and associated afterglow. And this is the signature of heavy element formation. And just with one detection of a neutron star merger with this electromagnetic counterpart has really changed our understanding of heavy element formation. In fact, it's pretty likely if you have some gold or platinum on your person right now that this was generated in the merger of neutron stars. So let's get a sense of the timeline. So this is for the 2017 detection. This is a sense of both the physics that's happening and then also our ability to detect these signals. So here we've got this neutron star merger. We've got a gravitational wave signal that we hope to be able to detect in future observing runs before they merge to get some early alerts that there's a neutron star merger that's about to occur. And this t=0 here, so this is the time that those two neutron stars have merged into a final object, which we think is very likely a black hole. And then about 1.7 seconds later, so you might have noticed in the last simulation, there's quite a lot of matter that's now orbiting this new object really, really fast. So this is going to accelerate particles in the form of a short gamma ray burst. So we're going to see this burst of extremely energetic photons that's going to go in perpendicular to the orbits, the orbital plane of those neutron stars. And then on the scale of hours, we're going to see this kilonova signal develop. And this is, again, the interaction of this really, really neutron-rich environment that's now around this new black hole. And this is telling us about the heavy element formation. And then on the scale of days and months later, we expect to see this X-ray and then radio afterglow. And now this is telling us about how this blast of neutron-rich matter is interacting with the interstellar medium around it. So there's really so much physics here, and we can actually get a sense of where in the sky this is happening just from the gravitational waves. So gravitational waves, unlike a telescope, where you can take a telescope and you point it at some particular part of the sky and you know exactly where you're looking. So gravitational wave detectors are much more like a microphone, where we're sensitive to most of the sky, but you're going to need more than one detector to try and triangulate where in the sky your signal's coming from. So this is why it's really beneficial for us to have a network of detectors all operating at the same time and to make essentially this sky map, this triangulation of where the signal is located. All right, so what else have we found? So this was a really, really exciting discovery. What else have we learned from gravitational waves so far? So I'm going to take you on a tour of the schematic. So the y-axis here is the measured mass of the object in solar masses. And the x-axis has no real meaning whatsoever. We try and organize it to fit everything on the plot, which is getting harder and harder, which is a good problem to have. But the colors do have meaning. So each one of these yellow dots here that you're seeing, so this is a neutron star with a mass that's estimated electromagnetically. So this might be a neutron star that's in a binary with another neutron star, for example. Each one of these red dots is a black hole with a mass that's measured electromagnetically. So again, you've got some black hole that's emitting light. So probably it's has an accretion disk that's then emitting X-rays. And then it's probably siphoning that matter off of a companion that's giving off light. So probably a massive star. So these X-ray binaries can allow us to estimate the mass of black holes in our own galaxy. And then you also have orange dots. So these are neutron stars estimated with gravitational waves, using gravitational waves to estimate their mass. And then finally, black holes. So these are, each one of these blue dots is a black hole with a mass that we've used gravitational waves to estimate. And you'll notice for all the gravitational wave sources, so they always come in triples because you have those two components, either neutron stars or black holes, that then merge to the final black hole. So we always expect them to come in threes. And another really exciting thing that I want to point out is this discovery of this intermediate mass black hole. So this is sitting right here that then merged to form something even heavier. And what I mean when I say an intermediate mass black hole is something in between the range where we'd expect to see a black hole from the collapse of a star, and supermassive black holes at the center of galaxies. So before gravitational waves, the largest mass from a black hole from a stellar collapse was roughly about 20 solar masses. And you can really see that gravitational waves have completely unlocked this pretty well populated mass regime that we're seeing here. And theoretical predictions told us that we might expect to see some kind of a black hole from a stellar collapse all the way up to roughly about maybe 100 solar masses. And here's the first time that we had really definitive evidence of a black hole that was above this limit. So we're starting to uncover some surprises. And something that's not obvious from the plot is how far away these sources are. So I'm going to transform this for you here. So this is a different version of the same plot where I've still got mass on the y-axis, but now here distance is in the x-axis. And here again, I've got my black holes measured electromagnetically. So those are in green. I've got neutron stars with masses measured electromagnetically in purple. And you'll notice that the majority of these are all within the Milky Way, with a few in the Large Magellanic Cloud or right outside our galaxy. But gravitational waves, all of these signals are much, much farther away. So the closest signals that we've seen, so this is the 2017 neutron star merger, but many of them are gigaparsecs away. They're billions and billions of light years away. So we're not only sensing this new regime in mass, so this totally different range of masses that we've unlocked with gravitational waves, we're also sensing much, much farther out into space than we could with light in terms of measuring the masses of these stellar remnants. So you may be wondering, how do we do this? So I'm going to give you a little tour of how the data analysis works with gravitational waves. So general relativity tells us, again, what the signature of the signal should look like. So again, we've got this in-spiral phase where the two black holes or neutron stars are orbiting each other. We expect this to be speeding up. We expect the frequency or the time between orbital cycles to be decreasing until they merge, and then that final object rings down. And we also know that since gravitational waves are so weakly interacting, that signal is going to propagate really, really vast distances, and we can expect to see this essentially unaltered. We don't need to account for dust or anything else that you might need to think about if you were using light to do astrophysics. And what we're going to do is we're going to look for our signal. So this is essentially our model from gravitational wave predictions from general relativity. And then I'm going to search for some tiny signal that's buried in my noisy data. So my noisy data is in blue, and I've got some tiny signal in here. And I'm going to essentially drag my model across my signal and compute how well they match. So this is called the cross correlation. So let's get a sense of what this looks like. So I'm taking my model, which again, I got as a prediction of general relativity, and I'm going to compute how well it matches my data at each one of these points as I'm dragging it across my data. And if I get a match, even if it's not perfect, you might notice that the model is not an exact match for my data, but I'm going to get what we call a trigger. So this is called a matched filter search. This is a really, really powerful technique that you can use if you have a very good model for what your signal is going to look like in your data. So let's say we have a candidate gravitational wave. So our next job is going to be inferring what is it? So where did it come from? How far away is it? So we learned a little bit about using triangulation to tell where it's coming from in the sky. So something else that I'm going to get, again, remembering all the way back to that very first equation. So gravitational waves is going to tell me about the distance of the source. So this is also something that's really special to gravitational waves. We're not really able to measure distance that well using light. So let's get a sense of what we're going to do here. So here is strain amplitude on the y-axis, and here's time. And I've got some noisy data here in blue. So this is actually real data from the first Nobel Prize winning detection. And then what I'm going to do is I'm going to evolve my model, which is yellow here. And what I'm going to change the mass of my model, and then I'm going to try to line that up with my data in phase. So once I've got a good match for the shape of the signal that's in my data, general relativity tells me how loud that signal was at its source. So all I need to do then is scale the amplitude of my data to my model, and that gives me a direct estimate of the distance. So let's see how this works. So I'm going to evolve my model in mass. So I'm trying to line up my model with my data in phase. This tells me what the mass was at the origin. And now all I need to do is scale that data, the amplitude of the data, and this tells me an estimate of the distance. So this is roughly how we're able to infer what a source was if we find one in the data. And we can really learn a lot of physics here. So because we get this distance estimate, we can use some kind of a measurement of redshift. So for example, for the binary neutron star merger, this had a host galaxy where we were able to measure the redshift very well. And this we can use to get this independent measurement of the expansion of the universe and maybe resolve some tension between measurements from nearby. So we from type 1a supernovae, for example, and conflicting measurements that come from the very early universe with the cosmic microwave background. So we can also get this insights into the nature of really, really extremely dense matter and neutron stars. So this is at energies far, far above what it would be possible to produce in a lab on Earth, with these the tidal forces of these neutron stars essentially tearing the stars apart. We can get a lot of insight into how those neutron stars are composed and packed. We can also test general relativity. So is general relativity doing what we think it's doing in this really extreme space-time curvature near black holes? And then, of course, we're also learning for the very first time the census of dead stars. So what's out there in the dark, and what does this tell us about how stars have been born and lived and died? So this is, again, very, very new as a field, and a lot of really exciting physics that's still yet to come from gravitational waves. So I'm going to spend the last part of the talk talking about how do we do this in terms of the instrumentation. So we're going to take a tour of a LiGO detector. So we're going to start zoomed out. So this is only about 2 kilometers for reference. That's the mid station. And again, those arms are 4 kilometers long, just to reinforce the sense of scale. So what we're going to do is we're going to take this flying tour of the detector. We're going to start from the laser source. So we're going to fly all the way into this, what I would call the pre-stabilized laser. So you're going to see a lot of jargon here. I'm going to do my best to explain it. So this is a pre-stabilized laser, or PSL. And this is going to be steered through a series of mirrors into the interferometer. And the first thing that it encounters is what I would call an optical cavity. So this is just a series of mirrors that are these 3 mirrors here in pink. They're essentially using resonance to select for certain features in the light. And then this laser beam is then steered into a second cavity that's in this yellow-green color. And this will serve a purpose later, but for now that light's going to go right to the beam splitter and get split in 2 orthogonal directions, just like we saw in our very simple Michelson interferometer. And now we're going to zoom way, way out so we can see all 4 kilometers of each arm. And at the end of each one of those arms is an optic, or a mirror. And that's going to cycle this light up as it's resonance or reflected about 300 times is the power increase that we get from, we call them Fabry-Perot cavities. And now we're going to zoom all the way out to the end station. We're going to take a look at one of these mirrors. And they weigh about 90 pounds. So they're about this big. And you can see these very thin fibers that are holding them up. So we use these to isolate the mirrors from ground motion, and also to isolate them in terms of thermal noise that we might get. So the light will cycle in the arms, and then finally it will come back to the beam splitter, and then again 50% of it's going to travel back to this first cavity that we saw here in green. So that's going to recycle the lights. And then there's another cavity here that's going to do something really similar on this side. And then finally my light makes its way to this photodiode, and that's where I'm going to read out my signal. So if I have a gravitational wave that's coming into the plane of the detector, you can see this stretching and squeezing of space-time, this relative change in length between the 2 arms of my detector. And as the light propagates through my interferometer, this is what it would look like. Essentially, it's what I would call the output port of my interferometer. And then this is tracing out, again, this the data from this very first detection of gravitational waves back in 2015. So there are a lot of really cool technologies that go into advanced LiGO in particular. So this is the gravitational wave detector that I do my research with. So this is strain noise amplitude on the y-axis and frequency on the x-axis. And there are a couple different frequency regimes where we have very different limiting noise sources. And I've just shown a snapshot of the kind of technologies that we use to push that noise down as far as we can. So we're really limited by ground motion at the low frequencies. The Earth is always kind of sloshing around. We have resonant modes from oceans. We deal with earthquakes. So it takes really sophisticated technology to isolate those mirrors from the ground. So what you're looking at is active seismic isolation. So this is essentially a platform, this sort of beam-looking thing that's sitting on top of these piers. So those piers are hydraulically isolating the structure, which is then supporting this vacuum chamber. So the hydraulics provide essentially they're going to float that structure that's going to provide one level of isolation from noise. But what we also do is we measure what the ground motion is doing, and we use modeling to predict how that motion is going to propagate to the structure. And we actually push on it all the time. We're always actively pushing on these platforms to try and isolate them further. So just like your noise canceling headphones work, we're also doing this with motion. And then here we're also limited by the very, very tiny molecular motions of the coatings on the surface of our optics, as well as the optics themselves. So this isn't limiting for us yet, but it will, we hope in the next observing run, we're going to push this other high frequency noise, which we call shot noise, which is a quantum mechanical effect that essentially has to do with counting. So we're in the business of counting photons. That's what we're doing at our output photodiode. And just like with any other counting experiment, the noise is going to go as 1 over the square root of whatever it is you're counting. So in order to combat this and to push this part of the curve down, what we do is we put more power into the interferometer. So that's just what we have all those recycling cavities for. So you saw the Fabry-Perot cavities, those are the arms, and then the 2 recycling cavities on either side of the beam splitter. That's what they're doing. And eventually we're going to come down to rest on this thermal noise, where now it's a material science problem, which is another really interesting and critical branch of physics that we rely on in order to take our data. All right, well, what do we get through all these really awesome technologies? So I'm going to show you to scale the sensitivity of the LiGO detectors. So we're going to start zooming around with the electron outside of this hydrogen atom. We're going to zoom all the way down to the surface of the proton. And what you're going to see is to scale what the relative distance measurements are that we're able to make. And so this was actually made, this animation was made in 2016 for the first announcements of the first detection of gravitational waves. We're actually doing about a factor of 2 better now. But what this is showing us is that our sensitivity to relative changes in length is about 10,000 times smaller than the diameter of a proton. So very, very, very precise measurements that we're able to make with LiGO and Virgo. And now our goal is to keep pushing this noise down. So here you're looking at the sort of similar curve to what we were looking at a couple slides ago. So with the ground motion limiting noise at low frequencies and this quantum shot noise at high frequencies. So here's how well we were doing in the first observing run. So this is again the first detection of gravitational waves. This was the very first detection of neutron star merger and this kilonova counterpart in O2, so doing a little bit better. This was our most recent observing run. So we had LiGO Livingston, which is in green, a little bit better than LiGO Hanford, which is in this red color. And even then, in this past observing run, we were observing about a signal per week. So this is where we were in the last observing run, and where we hope to be in the next observing run is 1 signal per day. So this graphic that you saw where gravitational waves are already starting to dominate what we know about dead stars, we're going to really start to see an explosion of new discoveries, 1 per day, all the time. It's going to be pretty tough to keep up with them, which is going to be a good problem to have. And then beyond that, we have other plans for extending the range of these detectors even further. but I'll give you a sense of where we are right now. So the 2 LiGO detectors in the US, as well as the Virgo detector in Italy, are undergoing upgrades. So this again means trying to push that noise floor down. So this is through both trying to increase the power that's in the interferometer and doing other quantum mechanical tricks to push the shot noise down, and also thinking about how to push that seismic noise down even further. So we were a little bit delayed from the pandemic. We were supposed to have started the run this year, but now it's going to be started in March 2023. So it's a really exciting time to get involved in the near future. That's going to go on for a year, that we're going to be seeing a gravitational wave signal every day, with a lot of exciting opportunities to think about corresponding telescope signals. And we also expect Cover to join. And I think I'm going to try and speed through the next few slides and give some time for questions. But I want to give you a sense that this is not the only type of source that we can detect with our current detectors. So here we've got essentially how well we can model the source, with this being really well and this being not well at all. And then also the duration of the source. So how long would that signal spend in the detector data, from milliseconds all the way to thousands and thousands of years. So we've detected most sources in this green range here. So most different types of compact objects, coalescences or CVCs. So this is the black holes and the neutron stars. We have not yet confirmed a detection of an eccentric system. So that's one more milestone that's ahead of us still. And something else that would be really exciting is a burst source that we don't have a really good model for. So something like a core collapse supernova, where we'd see neutrinos and gravitational waves and light all from the same source, would be a real treasure chest for us. And then there are also these really, really long duration sources. So this is a spinning neutron star, if you remember, all the way back to a neutron star with a really small asymmetry on it. So we expect to be able to see spinning neutron stars in our galaxy, and then maybe potentially some kind of a remnant background from the Big Bang in gravitational waves. And then, of course, there's maybe the most exciting thing of all, which is the unknown. So who knows what we might find with this totally new window into the universe. And something that's really different about gravitational waves than other physics experiments you might have heard about that maybe take place in the lab. So our collaboration is really big. There's over 1,500 of us, and that's just in LiGO. So we also have Virgo and Cover and other gravitational wave experiments out in space. So there's thousands and thousands of physicists all over the world that are contributing to this problem, which is one of my favorite aspects of working on it. And I wanted to give you a flavor of what it's like to do gravitational wave research. So here's a picture of a few of us from my lab actually going to the LiGO sites. So instead of having a lab in the building at UBC, we actually will travel to the LiGO detectors in the US and in the future in India as well. But we also go all over the world to meet with our collaborators. So travel is a really wonderful and exciting part of gravitational wave astrophysics. And in terms of what we do day to day, so here are some images of some undergraduate students who are looking at different aspects of noise coupling into the detectors. So they seem to be having a really good time. I always had a really good time when I was involved with LiGO research as an undergraduate. But we spend most of our time in my lab crowded around a computer. So we do lots and lots of data analysis. And I want to give you a really quick flavor for what undergraduate research can look like. And I don't expect you to understand these plots at a glance. It's probably going to take me way too long to explain them in detail. But just to give you a flavor, so we've had students like Sabiha who have been looking at how noise coupling from the environment is affecting the noise that we see in gravitational wave strain and how to reduce that noise. We have students like Helen, who's still working with our group, who are searching for this very first detection of gravitational waves from a galactic source. So this is trying to trace out the path of gravitational waves from a spinning neutron star. We have students like Nicholas, who are working on trying to really accurately extract the parameters of a source of the merger of two black holes. And then students like Sarah, who are looking at new ways to try and distinguish between signals and this really, really noisy data that we have for gravitational wave detectors. So I have a few more slides about the future. I suppose I'll leave it to Ben here. This may be a good place to stop and leave plenty of time for questions. or if you'd like to ask about the future, I'm also very happy to answer that too. So thanks a lot. I'm looking forward to your questions.
Wonderful. Thank you so much, Dr. McIver, for the amazing presentation on gravitational waves. This is personally one of my favorite subjects in physics, so it's a pleasure to be here and listen to your wonderful talk. Before we move on to the QA, please, everyone attending, we're going to have more talks like this. So make sure to register for our next session of the Physics Hour by Dr. Lisa Deng, and she'll be talking about exoplanets, so more awesome space stuff. So we'll now move on to the Q&A. I will